homework, and I'm going to put all the solutions to all the homework except those problems, which I'm going to give you a copy. I haven't written it in an organized way. So I'm going to give you that one after spring break for those problems. And the rest, I will put the solution online. When it comes to today's lecture, last week we discussed about the Maxwell stress tensor, and starting from the force on a given volume of charge when it's exposed to external electric field and magnetic field. Starting from that force, we were able to derive the Maxwell's stress tensor. Basically, force can be expressed. So this is all the derivation that we went through, and we ended up with finding the force density which is expressed in terms of the divergence of the Maxwell stress tensor and the time derivative of the Poynting vector. And the Maxwell stress tensor is expressed in terms of the electric and magnetic field tensors, which is given by that. So that's the Maxwell stress tensor. So this represents the electric field, and this one represents the magnetic field. So today we will see the application of this Maxwell stress tensor, find the force in an electrostatic case, which we already know how to find the force. And also we will talk about conservation of linear momentum and conservation of angular momentum. So the example that I'm going to do next, which illustrates the application of the Maxwell stress tensor, is going to be a little bit lengthy and probably a little bit difficult to follow up because it involves tensor, and as you know, dealing with tensor is kind of messy. So just remember that this is the equation that we use to generate the elements of the Maxwell stress tensor. So this is for the electric field, and that's the magnetic field. So this, just by changing I from 1 to 3, J from 1 to 3, you can generate all the elements for the Maxwell tensor, Maxwell stress tensor. And that's how we express the Poynting vector. So with this, let's go to the example that we are going to do, but first let's write the equation. In terms of Maxwell stress tensor, the force can be expressed as, well, actually the force density F, which is defined as dF with respect to tau, that is equals to the divergence of the Maxwell stress tensor minus 1 over the speed of light squared, the time derivative of the Poynting vector. So this was we derived last time. Yeah, so this is what we derived last time, starting from just the force on a volume of charge due to an external electric field and magnetic field. And we use application of the Maxwell's equation, of course, for the from the Gauss law and the Maxwell equation from Ampere's law. So using those two relations, and after going through some derivations, that's what we end up for the force density. So if I want to find the force, then what should I do? I have to integrate this over the volume. So the force, so this is the force density. So the force then is going to be F equals to the integral of the force density over the volume. So if you do that for the force density there, then what you'll find is F equals to the integral of the divergence of the Maxwell stress tensor d tau over the volume minus 1 over c squared, the integral over the volume ds by dt. So if we apply the divergence theorem here, I can express this as what? As a surface integral, right? So applying the divergence theorem, then I can write the force as an integral over a closed surface. Whatever surface you come up with that encloses the volume of the charge, when you integrate this stress tensor over the area dA, that should be the same as that. And minus 1 over c squared, now this is over d tau. So I can pull out the time derivative, then I can write this as d by dt of the integral of s d tau. So that's how we express the force in an electromagnetic field as well. So let's see the application of this equation for this example. You know how to find the force for this, don't you? Without using this. We have done this kind of, I think we have done this problem in ENM1. So here you have a solid sphere charge which is uniformly distributed over the entire sphere, and the total charge is Q. So, and the radius of the sphere is R. Your objective is to find the force created on the upper hemisphere, on the northern hemisphere of the sphere. So to find that, if you have to apply Coulomb's law, you just consider an infinitesimal volume in the upper hemisphere, and you need to find the electric field at that point, and then you multiply that infinitesimal charge with the electric field that gives you the infinitesimal force, right? And then you do the integration over what? Over the upper hemisphere. So that's how we did it. But now let's see if we can apply this and get the same result. All right, so the first thing is a static case. So that means the Poynting vector, which is, so where here the Poynting vector S is given by 1 over mu naught, the electric field crossed with the magnetic field. So this, in the static case, the electric field is independent of time, the magnetic field is independent of time, so you can't cross this one. So for a static case, then we know that d by dt of the integral of s d tau equals to 0. So all we have to